Today we are going to talk about the second fundamental theorem of calculus. We learned the first fundamental theorem a couple days ago, and that was basically how to find the answer to a definite integral, how to calculate area under any curve. Today's theorem is a lot like that. It is not a theorem to memorize. It is a procedural theorem, how you do a certain kind of problem. Okay? We're going to start out by looking at an unusual function and how this function works. So I would like you to please write capital G of x equals. The function is actually an integral. It is the integral from 0 to x of 2t dt. Now this function is called a function defined by an integral. And we're going to be studying these in more detail over the next week or so. A little bit at the end of this week and then again after Thanksgiving. Function defined by an integral, which I abbreviate FDBI. And we'll see FDBI on Friday when we come back to this again. Okay, that is a weird looking function. Yes, ma'am?
Why is the G of x instead of t?
Because when we plug in values for x, they're going into the top of the integral, and then we're going to evaluate the integral that way. Okay, it has to be written this way because whatever you plug in for x goes up here and makes this a definite integral. Right now, this is not a definite integral because it has an x in the upper limit. It's the first time we've seen this before. So what we're going to do is we're going to graph this thing and then we're going to evaluate points on it. So what I want you to do is draw a rather big graph. And it needs to be accurate as you can make it. So when I'm drawing graphs on notebook paper, this is just my suggestion to you. The middle of every line is 1 unit. And you're going to need to go up to about 6. Go about 6 in each direction. And then mark off your x-axis in about equal increments. You only need to go about 4 in each direction that way. So this is 1, 2, 3, 4. This is 2, 4, 6. I'll give you a second to do that. Okay. Now, let me read this to you in a little more simple English. The function g is defined as the area under 2t from 0 to whatever x value I choose. So the y value is found by finding area. Now, let's talk about this 2t. It has to just be a different letter than x. I chose t. That's the one that's most commonly chosen. What kind of graph is 2t? A line. What's its y-intercept?
0.
Its y-intercept is 0, and its slope is 2. So put a dot at 0, 0, and then go up 2 and over 1, making your line definitely go through those points. And then also do the same thing in the negative direction. So what we're going to do is we're going to plug in values for x, and we're going to see what the pattern becomes in y. Okay? So first of all, g of 1 means that I plug a 1 into the x of the integral. So g of 1 is the integral from 0 to 1 of 2t dt. Now, because this is going to make geometric shapes, we're going to look at this from a geometry perspective. Okay? So I want to know what is the area from 0 to 1 under my line. So draw a dotted line down from 1. I'm going to go ahead and shade that in. Can you calculate the area of that little bitty triangle?
Yes.
What will it be?
1.
It's going to be 1. 1/2 the base, which is 1, and the height is 2. So the answer to this, g of 1 is 1. What's G of 2? G of 2 is the area under the curve from 0 to 2. So that means instead of stopping at 1, I'm going to go all the way from 0 out all the way to 2 and find the area of all of that. So what's the area of all of that? Well, the base is 2, the height is 4, so it is 4. That area is 4. Do you see what I'm doing? Okay, let's do G of 3. That's the area from 0 to 3 under the line. So we're going to extend this up to 3, make my triangle even bigger. So now I have a triangle with a base of 3, a height of 6, that's 18, half of 18 is 9. Do you see a pattern emerging? Okay. The data, could you tell me G of 4 without me drawing the picture? What would G of 4 be? 16. 16, right? Okay. So even though I'm calculating area to find my Y values, they're still making a numeric pattern. Agreed? So I can now say that G of X, what's the function that G of X is defined to be?
X squared.
It's X squared. Very good. Isn't that interesting? Okay. Now, what's even more interesting is if you take this function G, which is X squared, and you take its derivative, what do you get? You get 2x. What was the line that we drew to find the area in the first place? 2t, which is really the same thing as 2x. So even though the function was an integral, it created an equation, and if I take the derivative of that equation, I'm right back where I started. That's what the second fundamental theorem of calculus does as well. Now, the second fundamental theorem is a theorem that when you look at it on a piece of paper, it is one of the ugliest looking theorems you will see in this class. It's just kind of scary looking because this function is in the theorem. So I wanted to introduce you to that function before you saw the theorem so you can kind of understand what it does. The function calculates area from 0 up to x. So this thing came out to be this thing right here. Okay, now I'm going to get a sticky note and I want to do something, but I don't want you to write this down. I just want you to watch. Okay, let's say that G of X is the same function we were dealing with a second ago. I want to look at it from an algebraic calculus perspective. Okay, I want you to do to this what we did 2 days ago when we learned the first fundamental theorem of calculus. I want you to take its antiderivative. What is the antiderivative of 2t?
T squared.
It is 2. T's power goes up to a square, and a 1/2 goes there. Agreed? From 0 to x. Are you with me? So now, if you plug in x for t, what do you get? X squared. If you plug in 0 for t, you get 0 squared. And we get the same answer, x squared, that we got over here. Do you see how that works? So the calculus and the drawing gave me the same function. So you could do it this way instead of doing it this way, but I just wanted to show you what it meant. Okay? So now I'm going to talk to you about the second fundamental theorem and show you exactly what it says. And the big deal about it is the fact that when you integrate and then you turn around and take the derivative, you're right back where you started. Okay, so let's write this down. And please tell me if I ever get my paper too far to the right and it gets cut off. Now I got to fix it under the camera. So here we go. Write this down, please. This is second FTC, the second fundamental theorem of calculus. It starts with the same phrase that every single theorem starts with. if little f is what? Continuous, exactly,
Yes.
on the closed interval from a to b, comma. I'm going to move it up some more. If f is continuous on the closed interval from a to b, then the function g of x, capital G of x, which equals the integral from a to x of f of t dt. Now wait just a minute. Doesn't that look like the function we just dealt with?
Yeah.
Yeah, looks very similar. But it has an a at the bottom, and the reason it does is that the bottom number does not have to be a 0. It can be any constant. So they put an a there. This function g has a derivative at every point x on the closed interval from a to b. That function g has a derivative at every point x on the closed interval from a to b. And the following is true. Now I'm going to change colors just because I want this formula to stand out. Okay? The formula said, I'm going to take the derivative of both sides of this thing right here. How can I write the derivative of g? There's two different ways. G prime is 1. We're going to use the one that's a little more obscure. We're going to use dg over dx. dg dx equals. Now, I need to take the derivative of an integral. That's kind of weird. I've never done that before. So what we write is a d dx in front of it, because remember that means derivative of the integral from a to x f of t dt. Now, I want to refer back to the previous problem. Okay. When we did the problem, when we did the algebra, we came out with g of x equals x squared. What was the derivative of my answer? It was 2x, right? And what was the original equation? 2t. So if the inside starts out as a f of t, what do you think it's going to be when I take the derivative? Any idea? It's f of x. The function stays the same, the letter just changes. Okay? Now, that is a very scary looking formula, yes?
Yeah.
Yes. Yes, ma'am.
Why does the letter change?
Why does the letter change? Because, let me screw this down. We started out with this being 2t, and we had to graph it that way. But notice that it was x, the number I plugged in for x, that determined what the answer was. So it changes to x's. Okay? Any other questions at this point? Yes, sir.
When you did a was 0, but what if it wasn't 0?
We're going to show you one of those when a is not 0, what happens. Because it is a constant, and you're taking the derivative of a constant, what is the derivative of a constant always equal? It goes away. It's 0. Yes. Okay. Now, I'm going to do something I don't think I've ever done in here before. Is I'm actually going to prove this theorem. That is something in college you're going to see a lot of. Your professors love to prove theorems. That's why I don't teach college, because I don't really like to do proofs that are complicated. This proof is a very simple proof, and it's very much like the sticky note that I just did. And so I want you to copy it down and see if you can follow them along with the math. That's what the professors want you to do. Now, if you choose to major in a math, they will ask you to actually do proofs yourself. You remember doing proofs in accelerated geometry? Oh. That was not my favorite thing. Okay. So here comes the proof. So copy this down, please. Proof. Here we go. We are going to start with the g function. So we're going to recopy g of x equals the integral from a to x of f of t dt. So recopy the g function. Okay, I am actually going to go ahead and take the antiderivative of the right side of that problem. Because I can, because of what we did the other day. What is the antiderivative of little f? Big F. So this becomes big F of t from a to x, right? Which variable do you, or which letter do we plug in first? X. So this can be rewritten as big F of x minus big F of a. Agreed? And I'm going to bring down the g of x because I'm going to need that later. Now, as you look at this, please remember that x is a variable and a is a constant. And the fact that a is a constant is going to come into play in a minute. Got to remember that x is a variable, a is a constant. So when you take the derivative, you got to treat it like what it is. All right, I'm going to move this up a little more because I see a couple of you straining to see. Okay, what I want to do now is I'm going to come over to the side and I'm going to basically rewrite this right here. Taking the derivative of both sides looks like this. So I'm going to write dg dx equals d dx parentheses integral a to x f of t dt, like that. And I'm going to work it out and show that it equals f of x. That's the goal of my proof. Now, I just figured out in the left-hand column that g of x equals this. This integral turns into this, right? So I'm going to replace the parentheses with what I ended up with here. So I'm going to write equals d dx parentheses capital F of x minus capital F of a. Okay. Are you with me so far? Do you understand how I got from the top line to the second line? Because that integral, I just figured out, equals the f's. Now, what is this ddx telling me to do to this? What does ddx mean I'm supposed to do? Take the derivative. So what is the derivative of capital F of x? Little f of x, right? Are you with me on that? Because it's a variable, you just take the derivative because it's a function. Minus, this is a constant. F, if a is a constant, f of a is a constant. And what's the derivative of a constant? Always 0. It doesn't matter what a is. If a was a 5, it's still 0. So my answer is f of x, which is what the theorem said it was supposed to be. Now at the end of proofs in math books, they tend to put a little square and just color it in and say that's the symbol that I'm done with the proof. I did it. Yes, ma'am.
Why is that little f?
Because over here, I said that the antiderivative of little f was big F. So the derivative of big F is little f. Because remember that antiderivative means you go backwards. Does that make sense? Okay, if this was like a 5, what's the antiderivative of 5? 5x. What's the derivative of 5x? 5. It goes back to where it started. Does that make sense? Okay. Any other questions? So I'm going to put a little arrow. This means done with the proof. Done with the proof. I stumbled across that in the multivariable calculus book yesterday. And they'd never seen that. My kids hadn't. So I said, I'm going to show you what that means. The little square means that I'm done with proof. So anything you read after that has nothing to do with the proof. Okay. So you're probably thinking, Miss Bell, that's all fine and dandy. Oh, who cares? What's the point? Why do we even have this theorem? Okay, it's going to make your life so much easier when it comes to certain kinds of problems, and it also proves a couple of things. So what's the point? So let's write it down. What's the point of this theorem? Okay, I'm going to do scrap paper again for just a second. I love sticky notes. The inventor of sticky notes was a genius. Okay, I'm going to start with the function 3. Tell me its antiderivative. 3x plus c, right? What's the derivative of 3x? 3. If I do an antiderivative and then I do the derivative, what am I doing? I'm going in a circle, are I not? Yes. Is that going to be true with every kind of function? Yes. If I put x squared here, the antiderivative is, no, the antiderivative. 1/3 x to the third, and then if I take the derivative of that, I'm back to x squared again. So that's the number one thing that this theorem tells you, is that derivatives and integrals, derivatives and antiderivatives, are inverses of each other. Okay? Number 1, integrals and derivatives are inverses of each other. They basically cancel each other out. Integrals and derivatives are inverses of each other. Screwed it up. Now, when we did this a minute ago, we did it with an f. Okay? What did we say the antiderivative of little f was? Big F. And what's the derivative of that? Little f again. So did I even need to know what the function was in order to get back to here? No. What this also shows is that every function not only has a derivative, if it's continuous, it also has an antiderivative. Every function is somebody else's antiderivative. Okay? So here's the way we're going to write that down. Every continuous function is the derivative of another function. Every continuous function is the derivative of some other function. And that means that every continuous function has an antiderivative. Pretty much every continuous function has a derivative, and every continuous function also has an antiderivative. So you can go both ways. Okay, now, theoretically speaking, that's pretty important stuff. But where is it practically helpful? We're going to take some problems that we're going to ask you to find the derivative of. There's a long way and a short way. And knowing every person in this room, the way you probably want to do it is the what? The short way. You want to do the long way?
No.
No, I didn't think so. So, a couple of them we're going to have to do both ways to show you how the short way works. And as soon as we do the short way, you're free to do the short way forever. Okay? The long way shows you how the short way works. Okay? First example, let me show you how this is used. I have a function y that is the integral from 0 to x of cosine of t dt, and the directions say find y prime. So we're going to do this the long way at first, which is not very long, and then I'm going to show you the quick one-step short way. So I'm going to write long way here, and short way over here. All right. The long way is to take the antiderivative. So y equals, I'm going to wait just a second because I see people still trying to catch up. Okay, the first thing we're going to do is take the antiderivative of cosine. What is the antiderivative of cosine? It is sine. So we write sine of t from 0 to x. So y equals, plug in the x first, sine of x minus sine of 0. So the function is really sine of x, right? Yes. I'm taking the antiderivative.
There we are. See, look.
Okay. It is so easy to get those confused early on. Later on you'll get it straight. But right now it's so easy to get them confused. Okay. The sine of 0 is 0, but it could be any constant I wanted it to be. Now, if I want to know what y prime is, that's easy to do. What's the derivative of sine? Cosine of x. Now I'm done. Okay. So that didn't take too long, but I had to take an antiderivative, then I had to turn around and take a derivative. So the short way, here we go. Okay, I'm gonna wait just a second, let you copy all that down because I'm about to cover it up for a second. Okay. How do the answer and what's inside the integral compare? They are exactly the same except what has changed? The t and the x. So basically what's going on is when you take the derivative of an integral, the variable changes. The x drops in here and changes the t to an x. That's basically what happened in the theorem, right? Here's the theorem. It went from f of t to f of x. Okay? So that is the short way. So if I have that as my function, y prime is the derivative of the integral of cosine of t dt. And so what happens is that x drops in where the t is, and I'm done. Is that always going to work? Yep. That's what the theorem says.
What if it's not 0?
What if it's not 0? When we did the proof, we had an f of a, which was not 0. It was a constant, but when we took the derivative, it went away anyway. Okay? So the bottom number does not have to be 0.
What if it's not x? Then it doesn't work.
What if it's not x? Like, what if it's what? What do you mean not x?
Like what if it's like 1?
If it's 1, it's just a regular definite integral. Okay? Now, we will do some problems where instead of x, it's x squared. We'll get to that in a minute. Okay? Yes, ma'am. Okay. All right. Now, so let's use the shortcut for the next couple of these. Y equals the integral from 1 to x of 1 over 1 plus t squared dt. I'm going to scoot it up. Y equals the integral from 1 to x of 1 over t dt. I want to know what the derivative of that is. Yes?
So I understand why we're doing this, but why is it so important for the integral to follow those conditions, like the x at the top and then the 0 at the bottom?
Because that's the only way that it will come out to be exactly the same function. The x has to be on top. You're bringing up a good question. Why does it have to be? It can be any constant on the bottom, doesn't matter. The x has to be on the top because when you plug it in, the top goes in first. We're going to do one in a minute where the x is on the bottom, and I'll show you what happens.
Okay.
Okay? Now, do you happen to know what the antiderivative of this is? Probably not. I have taught it to you, but you probably don't know it yet, and that's okay.
Is it log?
No, it's not log, it's an inverse trig function.
Oh, is it?
This is inverse of tangent. But with the shortcut, it doesn't matter. Because all I have to do is take this x and drop it in where the t is, and that's going to be my answer. 1 over 1 plus x squared, and I'm done. Because I'm going to the antiderivative, I don't care what it is, but then I'm taking the derivative again. And it goes right back to the same fraction that it was before.
Why does it do that?
It just does. That's because they're inverses of each other. Okay? So just throw the x where the t is and you're good. Let's do another one. Y equals the integral from x to 0 of tangent of t dt. Y equals the integral from x to 0 of tangent of t dt. Okay, the theorem specifies that the x must be on top, and it's not. But we learned a way to make it go to the top. What's the way to do that?
To make it negative.
To switch them and then make it a negative integral, and that's what we need to do first. So the first step is to write negative integral 0 to x tangent of t dt. You remember that property? That if you switch the limits, it makes it negative?
Yeah.
Okay, and now we can take the derivative easily. The derivative of an integral, they cancel each other out basically. All that happens is that the letter changes. So the answer is negative tangent of x. Questions?
So we have to choose a property to flip it.
No, we just know that whenever you need to flip your limits, just put a negative in front of your integral. That's the property. Okay, I want you to try these two. The first one is y equals integral from 3 to x of secant of t dt, and then do y equals the integral from negative 1 to x of t over the square root of 1 minus t squared dt. Okay. All right, now we're going to take it a little bit further and show you some variations of what could happen to this problem. We're going to now talk about how to do a problem like this. d dx, when the limits of integration are 0 to x squared of cosine of t dt. Let me move it up. So the question is, what do you do when this up here is more than just an x? What if it's x squared? What if it's sine of x? What if it's x cubed minus 5x plus 2? It could be anything like that. And you might think, oh my gosh, that's going to make it so much harder. No, it doesn't. What we are going to do is we're going to do this one because it's an easy function. We're going to do it the long way once. And that will show you what the shortcut is. So instead of me teaching you the shortcut right away, if you forget the shortcut, you can always go back and do it the long way. Okay. So, what is the antiderivative of cosine again? Sine of t from 0 to x squared. Okay, so we are now doing the derivative of, we plug the x squared in first, sine of x squared minus sine of 0. Okay, yes ma'am?
Is there an derivative for e to x?
It is e to the x.
It's the same thing?
It's the same
so
thing.
ln is the same thing?
ln, there is not one that we know.
Seriously?
There is one, but we are not going to talk about it in this class. Okay, now, take a look at the function that you have created by putting x squared in here. Because this is an x squared and not just an x, you have to use a rule when you take its derivative. What rule do you need? You need chain rule. So the answer to this is cosine of x squared times what?
2x.
2x, the derivative of the inner.
Okay, wait. So we're taking the derivative of each part. And
We're taking the derivative of this right now.
okay.
So the derivative of this is cosine of x squared times 2x. So right here, just that much, it looks like, oh, I'm just supposed to plug in x squared for the t, right? But I also have to do the derivative of the x squared. So anytime this is more than just an x, you got to take its derivative. Now, what about the derivative of the sine of 0? That's still just 0. So my final answer is 2x times the cosine of x squared.
So basically, you will put the x squared with t is that, then take the derivative of the x.
Exactly. And I was just about to write that down. You were right. You replace t with x squared and you multiply by the derivative of x squared. The derivative of the inner. Do you see what I wrote down? So we replace the t with the x squared, that's given, but we also multiply by the derivative of that x squared. So that's the only change about doing it with an x squared. Yes, ma'am?
I don't really understand what's happening with the old chain rule. but that's
Okay.
what it is.
Okay. So let's go back to here. No, let's go back to here. Right here. Do you see that this is outer inner?
Yes.
Okay. So what is the derivative of sine of something? It's cosine of something times the derivative of that inner function.
Got it.
Okay?
Yeah.
All right. So, we are now going to do another problem just like this. We're going to go straight to the shortcut, which is what I wrote down right here. Okay? Let's practice one of these the short way. Can you see what I'm writing? Barely. Let's move it down. I want to do d dx integral 3 to x to the 4th of secant t dt. We're doing the shortcut. Okay? The shortcut says the exponent goes in place of the t. So I just write secant of x to the 4th. And then I multiply by what? The derivative of this x to the 4th, which is what? 4x to the 3rd. So that becomes, bring the 4x to the 3rd to the front, and you're done.
This is kind of easy.
It is kind of easy. Now, you could think of the old ones the same way. I don't care what x this is. You plug it in and you take its derivative. If that was just a plain x, you would plug it in and multiply by 1. The last variation is this. d dx integral x to x to the 3rd cosine t dt. Okay? How is this one different from the ones we've done to this point? There's 2 x's. So we got to talk about how do we do those. Okay, so I'm going to circle the 2 x's to let you see that there are 2 of them. Okay, we're going to do it the long way to come up with the shortcut. Long way, that becomes sine of t again. X to x to the 3rd. So this is now d dx of sine of x to the 3rd minus sine of x, top minus bottom. So now to finish this, we have to use chain rule with this one, don't we? So it's going to be cosine of x to the third times its derivative, 3x squared, minus cosine of x times just 1. And we just bring this 3x squared to the front. And we're done. So who can explain to me what the shortcut is to go from the first step to the last step in one jump?
The same thing. Twice.
Yes, but what do you do with the two answers?
Subtract them.
Subtract them. Malia?
Talking about the shortcut?
Yes.
Okay, well, what I was thinking is that you plug in, so you do the same like you did the example above that, you plug in the x to the third power and take the derivative, then you take the bottom x and then plug it in, then you subtract it.
Exactly. And what you need to remember is the order in which you do it is top minus bottom. Remember I told you top minus bottom is huge for the rest of this unit and for the rest of the school year. Top minus bottom. It's the top thing minus the bottom thing plugged in. Okay? So, I'm going to do one more of these with the shortcut, and then you're going to do one. Okay? d dx integral sine of x to x squared ln of t dt. I'm going to scoot it up. That's way down low. There we go. Okay. We're going to do this one together, and then you're going to do it by yourself. No, second to last. Okay? All right. Which one do I plug in first? The top one. So it's going to be ln of x squared times what?
2x.
The derivative of the thing you plugged in, 2x. Minus, now we plug in the bottom thing, ln of sine of x, times its derivative. What's the derivative of sine?
Negative. Oh, no.
Just cosine. Okay? So this is 2x ln x squared minus cosine x ln sine x, and we're done. So the shortcut sure makes life a whole lot easier. Okay? Now, your practice problem on the shortcut, and we will be done for the day. You try this one. d dx integral from x to e to the x of sine of t dt. Your turn. It is e to the x sine of e to the x minus sine of x. And that's it. How many of you got it right? Let me see. Awesome. Okay. This is it for today.